Uh, so this course is taken by Professor Vineeth, and the part of this course is divided into three parts. One is like introducing the course for the basic image processing, and then introducing neural network for the image computer vision stuff, and later they started with this sort of advanced techniques that can be used for the computer vision, um, beyond general neural networks. So these sessions are arranged by NPTEL people to do basically two things. One is that if you have certain doubts about that week, you can ask here. It will be answered directly, or it can be answered in the next session. Or if you second thing is that if you have doubt in like any particular topic that was covered in previous week, that you can also ask. The third thing is that third thing we can do is in this session is that we can go for solving some questions of previous year assignment. So we are strictly like instructed to not to solve this year assignment before the deadline. So we'll not be solving any this year assignment. We'll be always be solve. We can always solve, pick some problems from the previous year questions and solve that. And also, like apart from that, we can also go for like some code walkthroughs or some code tutorials that is there in the course, and the that correspond with the course uh, from the uh, GitHub repository shared by the instructor. So these are the few things that we can do in these sessions while tutoring, while giving the tutorial for this NPTEL course, Deep Learning for Computer Vision. So for today, today will be the first session. So it will be a bit relaxed, and I'll be like discussing what the course is and how it will flow. So bear with me if you have any doubt in the first week's lessons. Let me know. I can start discussing that as well. So basically, what I would say that before the commencement of deep learning, this before commencement of deep learning, there were a lot of work has done around image processing and image um, how to represent image, how to process image, how to edit image, and how to sort of extract certain features such as edge, then curved lines, or like blurriness, how to blur the image, and how to extract all these features out of the image. So there were very handcrafted methods. There were very there are very trivial methods that were used to extract features and like sort of uh, work on them. But after this the era of deep learning, everything is automated now. This edge extraction or feature extraction in general, and getting an inference out of the image is all automated now. So but first 2 weeks are heavily depending on this. So today we will be doing this tutorial session for week number 1, and subsequent week will be discussed in the coming weeks. So if you see week number 1, it discuss the history of image, the history of this image formation, and how images are captured earlier, how to represent an image, how to do a filtering on top of image, and how to convert the image from one image to the next image. So so if you like if you have seen, so someone reply in the chat, what is the till what point you have watched the video in the week 1 lessons? Is it like you haven't watched, you didn't get any time, or you have watched everything, or you still are watching in the middle way? What is the status of these videos of week 1? Okay. Yes, no one is replying, but I just completed intro of week one. Intro is okay. I see. So I just discuss briefly what is discussed in the week one content. Then you can go ahead and watch the lectures, and you will be able to understand it clearly. The week one, so there is a history, like chapter history video. I did not go through that video in depth because it's just history. And if you get any doubt, you can talk to me. I can refer and who like solve your resolve your queries. But what happens is the representation of image. So the story starts from this representation of the image. So let's say if you have an image, and so let's say if you have an image and image of a, let's say, cat, not a very nice cat, but still image of a cat, and you want to store this to a computer, or you want to store this and view it in your mobile. So how to go about it? How to go about taking an image and sort of storing it? So you can say that an image is consisting of pixels. So there are pixels here. If there are like 1,000 pixel in this direction and 1,000 pixel in this direction, so you can say there is a 1,000 cross 1,000 image, which is around 10 to the power 6 pixels, or 1 million pixels, or 1 megapixels. So it is very easy to represent the image, and by representing image you can, since it is a black and white image, so this is a image of a black and white cat, and since it is a black and white image, it is very easy to represent it using a 1,000 cross 1,000 matrix, and where the value of this 1,000 cross 1,000 matrix, so any value of this matrix ij mij is between 0 to 255. So this is this grayscale range where the value 0 means white, sorry, where the value 0 means black and 255 means white. Sometimes they normalize this to in the range 0 and 1, where 0 means black and 1 means white, and all the other values are squeezed in between 0 and 1 to represent this grayscale image, as an as a representation of the image. But uh, so this is the story of grayscale image. So 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 then how about the colored image? So if you go to colored image, so the story of colored image is something different. So you see that in colored images, so there are three channels. One is red, one is green, and one is blue. So if you see, and any color image is consisting of these three channels, and we represent an colored image using this three-dimensional matrix, where the each dimension represent a color, and any image that you see is a combination of the values or proportion of these three colors: red, green, and blue. If you see something intermediate colors, it should be something like some weightage to red, plus some weightage to green, and plus some weightage to blue. So any color can be represented as a combination of red, green, and blue. So the question arises, So then if this is the thing, the image size is say, let's say 1000 cross 1000 cross 3. The question arises that if this is the case, then then how about the other colors? Like you see, in the rainbow, the fifth gear, there are like 7 colors. So what happened to other color bands while while representing an image? This image could have been a band of 8 things or 10 things. So the reason it is not is a combination of all these colors is that so these are the things that is available in nature. But while we represent an image or perceive an image as an human, we only can capture three color bands. So if this is the color band, so if you plot this plot the graph where humans are perceiving, it is like this. So it is like it can only perceive three color bands, and in case of mouse it is something around 7 or 8, which can perceive more color bands as compared to humans. So this is all about like how to represent color image and black and white image. And when you say a HD image, you are talking about 720 pixel image, and for a full HD it is 10. So I just write it clearly in the bottom. For HD, an image has to be 720 pixel, and for full HD, it has to be 1080. And when you say 4K image, it is like 4000 pixel, 4000 pixels. So this is the way we represent the image in our image domain. And this red, green, blue also, the value of red, uh, the red channel varies from 0 to 225, green channel also 0 to 225, and blue channel also 0 to 225. So this is the way we represent image. And so is there any doubt in this section? Here you are more than welcome to ask this. And if you don't have any doubt, just type understood. Great. Now we'll discuss about this you know, another way of representing an image. So talking about image density, density of an image at point inj can be defined using some function, and it will be a distribution above this image, and a real world image is something that is sampled from this image density function. So let give me 1 minute. I'll just take. Yeah. So I was telling another way of looking at this image is that if the image is say 1,000 plus 1,000 plus 3, it is very safe to say that an image is a uh, 10 to the power 6 dimensional data. And if we can define the 10 to the power 6 dimensional distribution, we can say that any image is something that is sampled from this distribution. So if there is a n-dimensional distribution, you can actually sample one point from the distribution, and an image is like that. It is sampled from a distribution. Any real-world image is sampled from an underlying distribution. So by that definition, an image can be treated as a continuous density where each point has some density that is sampled from an underlying distribution. So this is just another way of representing images, but most of the time we will be dealing with these RGB values and nothing much. Then coming to the next uh, thing, we can see that uh, transformation. So let's say there is an image, and we're sort of trying to transform this to another image. So what sort of transformation that we can do? So one example that was given in the lecture is the changing the contrast of the image. So if your image have some values, you can actually change the contrast of the values by doing some operation. So make sure to watch all those videos for the detailed explanation of the same. But I'll just briefly describe what transformation. Uh, what do I mean by transformation? When I mean like transforming an image. So if you have an image and you want to make some transformation on top of it, so what are the way you can transform? So first way is that point operation. First way is the point operation. In point operation, you take this point and you make some changes to this point to get the corresponding point in the transform image. I'll just draw these lines for continuity. Yeah, not very straight line. Yeah. So if you have a pixel in your initial image and you add something or delete something or reduce this value to get the target pixel, it's called pointwise operation, where you are just taking the initial pixel and making some changes to it to get the final pixel. So let's say for reversing the contrast, so let's say you have so contrast means that contrast means like how bright a color is. So for reversing a contrast, let's say the new image is I dash, and any pixel m naught and n naught in the new image will be like taking the maximum intensity of the image and subtracting the intensity of that M0 and N0, then adding the minimum intensity. So this is a operation for reversing the contrast. What you are doing is that what you're doing is that so you're taking an intensity of an pixel. So let's say you have a white pixel here, here. Okay, you have a white pixel here, and its value is 255, and you want to transform this to something else, and so let's say its value is 200. So what you will do, you will subtract this value from the maximum intensity this pixel image has, and from that you will get the maximum is Imax is 255 because it is for any image. So you will get 255 minus 200, that is 50. Then you add the minimum intensity, which is 0 for any image because black is 0. So and you get 50. So your intensity was earlier 200, and so I'll just write it down. So Imax is 255 minus your current is 200 plus 0, which is 55. So your intensity dropped from 200 to 55. It's sort of saying you are reversing the intensity, the contrast of the image. So this type of operation are called pointage operation, where you take an image, you take each and every point of the image and you make some transformation to that point, so that it will be reflected in the corresponding point in the transformed image. So this type of operation uh, uh, is called point-wise operation, point operation, and so it has achieved a lot of things, like in the point operation. Then comes the local operations. So then comes the local operation. So in local operation, what happens is that in an image, a locality of pixel decide what will be one target pixel. So value of one pixel's value will come from not from one pixel, but from a locality of pixel. So for example, if you are computing I hat 5, 5, what you will do is that you will take all the pixels that is there in the neighborhood of 5, 5, like taking I equals to 5 minus 1 to 5 plus 1, then j equals to 5 minus 1 to 5 plus 1, I, and j. So what you are doing, so let's say the 5, 5 pixel is here, and its value is 2, its value is 1, 1, 2, 3, 1, 0, 0, minus 1. So what you are doing, you are sort of traversing, you're taking traversing in I minus 1 to plus 1 and j minus 1 to plus 1, and you are sort of adding all these values, which comes around 1 minus 1 plus 0 plus 0 plus 1 plus 3 plus 2 plus 1 plus 2, that is 0, 4 to 6 to 8. So value of this is coming from a locality that is called local operations in an image, where you take multiple pixels to decide the future of a single pixel in the next image. And third thing is called Global operations. Global operation is equal to local operation. Where the neighborhood is the entire image. So it's like uh, you take an image, you used all its value to compute a pixel's value in the next image. So that is called global operation, and we use this global operation to sort of uh, decide, while making a decision which requires everything from the previous uh, image. So these are all the sort of like operation that we have in an image while transforming an image. So if you have any doubt in terms of this, you can I can stop now and you can ask me right now. Yeah, I hope there is no doubt because no one asked. If you understood, you can also write understood or yeah, I got it or something. Okay, great. So I'll just give an example of local operation, that is moving average smoothing. So given an image, how do we like calculate the moving average and smooth it? So it's a very it's the same function that I wrote here for this, but a bit general one. So the example of global operation is Fourier transform, and for the example of local operation, I will write this function that is called moving average smoothing. Local operation. Well, moving average smoothing, and in the moving average smoothing we write the I cap or the I new, the new image, its x and y pixel will be equal to summation of I equals to x minus k. In that case it was 5 minus 1, k is 1 and x is 5, to x plus k, then summation of j that varies from uh, y minus k to y plus k, j into 1 by 2k plus 1 squared. So it's like saying if you want a image this point value, what you can do is that you can go in this direction minus k, this direction plus k, this direction minus k, this direction plus k. So you take all the values that is there and add it and then subtract it by the like subtract it by the number of values that you take. Like if the value of k is 1, it is 2 into 1 plus 1 square, which is equal to 9. So you divide everything by 1 by, so you multiply everything by 1 by 9. So just a average, taking average. And if you have a filter like this, so if you have a filter like this, what you do is that you just put this filter here, and for the next time you put this filter here, put this filter here, and you get the corresponding values in the image, where you sort of move the average value in the corresponding in the produced image, where you can see that you will be able to smooth out the discrepancies that you can see. So actually, if you see the slides, if you see the lectures, there Sarah mentioned that how there is a white spot in the black area, and by doing the moving average, it is all blends out nicely and give us a nice image. So it's a very good way to smooth out the noise in an image. Yeah. So now we will discuss I hope this is clear, and there is nothing that I spoke of new. So I will be moving forward with our discussion, and so after 1 hour, like after around 7, we'll take a short 5-10 minutes break, because 2 hours is a long session. So we'll take a 5-10 minutes break. Then we'll again start at 7:10 or 7:05 or 7:10, and continue our discussion on the rest of the topics that we have. And next thing that I'm going to discuss is image histograms. So talking about image histograms, so let's just first draw an image. So let's say I have a grayscale image. And there is it's an image of a cat. And all these pixels have different densities. I got a question. Can you please explain about whether a kernel is separate, in which condition is not separable? Sorry, this is my first session. Can you please explain whether a kernel is separable, in which condition it is not separable? So I didn't get your question actually. Like separable, not separable. Like I don't think there is a definition of separableness in terms of kernel. So if you could give me more, like more information on the same, I would be able to comment on the uh, question that you asked. Okay, so I'll take that question later. Okay, so did you ask a question? Yeah. Yeah. Okay. So yeah. So the question that you asked now is
Okay. Okay. When kernel is separable. In assignment, there is a question 1 by 256 matrix, whether it is separable or not. So kernel separability is a different study. We haven't reached there yet, but I would say that you can separate the kernels depth-wise as well as spatiotemporal way. So, uh, depth is separable. Kernel separableness is something like if you separate a kernel into two or more kernels, can you achieve the same result with the disk, with so is it possible to achieve the same result with fragmented kernels as with the original kernel? So if it is same, then that is called separable kernel. If you cannot achieve the same result by dividing the kernel into many parts, it is called non-separable kernels. So actually, but how exactly? So to answer that, I might not be able to answer this question whether 1 by 156 matrix is separable or not, because we are strictly instructed to not to discuss the assignment questions in the doubt clearing session. If you have any doubt regarding the concept, I can go in depth while I'll cover the kernels, but I don't think I can go in depth about the question right now. Uh, okay, thank you. Yeah, so this thing that I showed here, this filter, uh, so this sort of moving in this image, we can put instead of just taking the average of this image, we can weighted average of the image. Yes, someone drew here. I think someone drew in the screen. Are you able to see this drawing in the screen? I'm able to see the drawing in the screen. It's quite disturbing. I cannot control, I guess. Let me see if I can disable this drawing. I I removed it. So yeah. Okay. So what we are talking about, we're talking about kernels. So kernels I will discuss in some time. So before discussing kernels, let's just start with image histograms. So when you have an image, let's say grayscale image, because it is very easy to understand with grayscale images. So you have pixels of gray, you have pixels of black, pixels of white, you have pixels of in between. So you have pixels of values that varies from 0 to 255. So what you can do is that if you put plot something and its x-axis will vary from 0 to 255 and its y-axis will depend on the number of pixels that you have in the image. So what you can do is that you take all the pixels, you count all the pixels that has intensity 0, you plot that. You count all the pixels that has intensity 1, you plot that. You count for similarly for 2, 3, 4, and if you start plotting like this, and you get a plot like this, and this will be a histogram plot, and it will represent, and this histogram will represent what is the number of pixel that is present in a particular intensity. So and if you could normalize that, if you could normalize this, then you can actually see what is the percentage of pixel that has intensity of, let's say, any intensity I or K. So this is called image histograms. It's a very simple thing, but it's a very useful thing to remember. So yeah, so this is the image histogram. And one associated topic that is connected to image histogram is called cumulative frequency graph, CFG. And cumulative frequency graph is also a graph where it's kind of a line graph where any point in this graph, so this x-axis is again intensity, here also intensity, and it is count. Here also the x-axis is intensity and y-axis is cumulative frequency. So x-axis is intensity, and you take this x-axis. So if any point in this curve will represent what is the number of pixel that has intensity, so number of pixel having intensity less than or equal to this point K. So it's like a cumulative sum of point that have intensity K or less. So this graph will always grow up, and at some point it will converge to 1 because the total number of pixels can be anything, but when you normalize this graph, it will be 1. So maximum number of pixel is 1. So like you are like normalizing it to 0 to 1. So hence so that will be 1. So this is the cumulative frequency graph of an image. So the two major thing, one is histogram and second one is cumulative frequency graph. They are two very important thing to remember, like this two. This one I would click now, refresh. Yeah, histogram and cumulative frequency graph. So there is something called contrast transformation. So by contrast transformation, you take an image, you transform it contrast to something else, or something pretty, like something pleasing. So if you take an image I and take an image I, if you want to convert it to I cap, and if you just put it a linear line, then it is saying that every pixel in ith location is same as this ith location. So it's like a linear transformation where if you are not changing the image. So if it is half, it should be half. So if you really want to make this image beautiful, what you need to do is that you need to lower the probability of pixels which are lower intensity, and increase this pixels intensity which has higher intensity. So it's like enhancing the black and enhancing the white in an image. So when you if you remember, when you are editing any image in an image editing app, you always see this curve and you have to drag that curve, and I spend a lot of time in my childhood to figure out what, like earlier, to figure out what this curve represent. This curve is actually this intensity curve, and when you drag down the initial or this lower end of the curve to this down and upper into the up, you can realize that you are making the black pixels more black and white pixels more white, so that the difference will be very clear and you can see a very nice image. So this is called contrast transformation. We are sort of transforming the contrast, and now you will see we'll see how we can use histograms to histograms of the image, and how we can use the how we can use the contrast, so cumulative frequency graph, to adjust the contrast of any image to make it more enhance make it more enhanced, and making it more uh, uh, making it more appealing. So this process is called histogram equalization. In the lecture, Sir didn't go in depth in this topic, so we decided that we will discuss this topic in the tutorial session. So yeah, so I guess we have 1 hour is already gone. So we'll take a short break of 5 to 10 minutes, and we'll meet again sharp at 5. Sorry, 6, say 7:05 or 7:10. Thank you. Do not leave the meeting. You can just keep the meeting on and uh, take a rest, bathroom break or something. 5 10 minutes. Bye.
equalizer, and this concept came for sort of creating clear images out of blurry and non-interesting images. So I'll show you an example, interesting example. Here, here, here is an example of histogram of intensity that I can find for an image. And what I want is that I want to do this transformation T, which take this bumpy image, like there's a intensity of this image where this is higher, and I have to take this and I have to transform this to like this. So why do we care about this histogram equalization? Because let's say we have a original image like this, and if we change this to if we equalize the if we applied histogram equalization on this image, we'll get an image something like this. So the advantage that we're getting out of it is that we are sort of taking the so how we are getting it, I'll derive it later, but what we're doing is that we're sort of taking an original image and we're sort of adding the contrast, we're sort of lowering the uh, uh, smaller value contrast and adding the larger values contrast sort of it and getting this. So yeah, so let's say this is the original image, and the red lines are the histogram of the original image, and these blue lines are the CDF, or the cumulative density function of the image. After the histogram equalization is applied, all these things will be evenly spaced and distributed sort of uniformly around across the this intensity range. And in histogram equalization, the CDF always try to be a straight line. By straight line, by straight line, you can see that the number of pixel in the low density region will be lower, and the number of pixel in the high density region, intensity region, like the number of pixel in the low and the high will be will become similar. So that when you do the cumulative distributed cumulative distance density function, it will increase linearly with the intensity. Not audible. Thank you for pointing out. I guess my earphone was pointing backward, so I couldn't. I do not know that. Thank you for pointing out. So this I was discussing about histogram equalization and how we can how what happens when we do the histogram equalization. It sort of try to evenly spread out the histograms, the density histogram, the image histogram across all the intensity levels, and it tries to do a uniform distribution on the intensity levels. So derivation. So let's come to derivation of this histograms, like this histogram equalization. So I'll say that histogram equalization. Yeah. Uh, so let's say, so I'll just take this thing from this image. Yeah. So let's say there is an image I of size m cross n, and let's say the I max with the maximum intensity of that image. that is 255, and HI be the histogram. HI be the histogram. So HI be the histogram of the image. So sorry, not this HI. HI. So this histogram is a function of image. So HI is the histogram of the image, and so it is saying that the output image that you will get, the ith and jth pixel. So the pixel correspond to ith row and jth column will be the maximum value of this, the maximum intensity of this image, which is 255, and maximum intensity value, that is 255 into the CPPIJ, which is the cumulative frequency for that pixel range. So let's say the images cumulative frequency curve is like this. So if you want to change any pixel that has the intensity of k, what you have to do is that, so uh, that pixel's new intensity will be the k into I max. That's the exact same thing that we did here. What we did is that we take the maximum intensity and we multiplied it with the cumulative frequency of cumulative frequency, so value of cumulative frequency graph for that pixel intensity. So we picked uh, this value, and we multiplied this value with the maximum amount of intensity that is possible to get the intensity of INJ. So given that, so CK is this, so this equation here is the equation of uh, density, this cumulative density function CDF, and it's the same as saying taking maximum and, like, adding to this. So by this, what we are doing is that if the we're sort of like uh, taking the maximum and like scaling it across the density range, so that we'll get a straight line out of it. Yeah, and this is how we compute our uh, histogram density. Yeah. So this is just a derivation to show that histogram density, histogram equalization makes the target image uniform, redistributed across all the intensity rays. Make sure to check it out if you want the derivation as well. So here are some examples of histogram equalization. This is a picture of IISc, which is not very clear. It is very dark image. When you do histogram equalization, you sort of try to distribute the intensity across, distribute the count of pixels across all density levels. So, and the resulted image is um, pretty nice, I would say. Next question is like, can histogram equalization always work? If you see this picture, there is this black lion that is lying, and if you see the graph of this, you can see most of the pixels intensity are concentrated across 0, and almost none of them are towards 250 or the maximum intensity. The answer to this question will be no. Histogram equalization will fail here, because since most of them are considered in 0, when you when you take the histogram plot, that will come something like the cumulative distribution plot, that will come something like this, and the maximum value is 1, will come like this. And if when you multiply something, if you want to multiply this thing with the Imax, this k multiply with k, nothing much will happen, because all these values will again come same. So these values will be same, and it will be all bright, So that's why you can see the lion is whole bright now, and the like you cannot really get a nice picture out of histogram equalization. So yes, the if the density of pixel is somehow distributed across the intensity levels, it is you are able to extract a very nice picture out of it. But if it is like just spiked across some pixel levels, you'll not be able to do that properly. Okay, then talking about linear filters. So, talking about linear filters. So this is all about the histogram equalization. If you have questions about it, you may ask now. I'll give 2 minutes for everyone that who were present in this session to ask questions uh, about histogram equalization technique that we just discussed. And this is not discussed very in an extensive way in the lecture. The professor sir said that it's kind of a homework to read. So okay, great. No questions. Yeah. Then we will move our discussion to linear filters or linear transformations. So when we discussed local operations, point-wise operation, and global operation, there we discussed about how we can how we can sort of how you can sort of affect a area of image to decide the 1 pixel's value in the target image. There we were sort of looking at how to take average or how to take maximum of an area. So here what we will do is that here given an image, input image, we will take into account a filter, or we term it as kernel, or we term it as also mask as well. So given a mask and given an input image, how the target image will look, what we can do is that we can take this filter, we can do pointwise operation on a local area, and then we get a value and put it in the output, and then we can slide the filter across the image to a different location, the next location, and do the same thing to obtain the next value. And this sort of is called like convolution operation, when we are convolving this filter using convolving this filter across the input image. So the question that she was a girl was asking, so what is separable and what is non-separable filters? So if you have a large filter, let's say, and you sort of uh, divide that filter into two or more filters, and if you can get uh, the same exact thing even after breaking the filter into two or more part, then it is called separable filters. If it is separable filter or separable kernels, if you cannot achieve the same result after breaking the filter into two or more pieces, then that is called non-separable kernels or non-separable features. So that is a definition of that. You can find more on this on the lecture itself. So for now, I'll just discuss how this a linear filter works. So what happens is that they will some linear wise so pointwise operation will happen. Let me see. So this is the filter. You see this 5 is in the middle, and -1, -1, -1, -1 is in all the four sides. And if you sort of think about it like this is addition of this filter and this filter. So the question is like, what this filter do? So in the literature, we have filters for everything. We have filters for sharpening the image. We have filters for blurring the image. If you just take the filter and pass it through the image, it will just blur the image. if you take that filter and like pass it through the image, it will like sort of sharpen the image. Also, there are feature for there are like filters for finding the edges, vertical edges, finding the horizontal edges, and everything. And this feature is
Yeah.
used for like sharpening the image. Why sharpening the image? Because you see all these so it's like so it's like taking an image and maximizing one value and minimizing all the value that is found in the neighborhood, and this is somehow like sharpen the image. So there are like lot of these filters that is available. If you could Google it, like what is the filter for sharpening image, what is the filter for blurring image, you can find a long list of these like these filters. Another question, like I wish to ask, like if anyone could guess in the participant, the three participant that is there, what is the filter that okay, what is the filter that we use to suppose it's an original image, I would shift the pixel one to the left. So what is the what is the filter that I should use, or that I should take into account while making this operation uh, operation. So if anyone can reply in the chat, I will be more than happy to know. Otherwise, I'll just go to the next slide and show the result of this question. Okay, so I'll probably like show the result. So this is this filter. So if I may like try it on the board. So let's say you have value of 1, 1, 2, 3, 4, 7, 0, 0, 2, and your filter is this one corner of an image, and the filter is 0, 0, 0, 0, 0, 1, 0, 0, 0. 0, 0, 0. And when you multiply this entire thing with this element wise, you'll get so this is a corner of an image. So this is like a corner of an image, and we're multiplying it to get the value of pixel of this corner, but this middle element. So we multiplied this and everything will be 0, only 7 will be left. So this value will be 7. So if you see, the value of 7 was here, now it is moved to the middle person here. So it's like it is a filter for a left shift operation, and similarly, if you want a filter for right shift operation, the filter will be like this: 1 0 0 0 0 0 0 0, and this value will be evaluated. Filter will be used to evaluate this value. So this one, the pixel value will come to this center. It's a right shift operation. So it's the filter for shifting. So you must have get like you must have got the idea that how sort of these filters are used in conjecture with the target function that we wish to evaluate, and sort of we get this uh, nice filters for every task that we have. So I think the next slides are uh, like a bunch of questions like if image thresholding can be used as a filter, or like if image if median operation can be used as a filter. But I guess this is this if something can be used as a feature or something cannot be used as a feature is more of sort of it's more of saying like if something can be used as a feature or not, it is more of saying like you have to see if it is satisfying some properties or not. If it is, if the property if the thing is not linear, or if the thing is not locally linear, then you cannot actually so if it is not linear, it is non-linear. That is like if you take I mean the function of a plus b should be equals to function of a and function of b. If it is not, then you cannot really ask, you can't really use this as a filter. So it's just a bunch of two different things. I'll not discuss much about this. I guess I covered a lot because in the course itself, in the first week, there was course introduction, then there is history, and then there is image formation. I described about image formation, how image is formed, how we represent the image. So image representation I discussed. I didn't discuss the image formation because it was optional. So image I discussed about image representation. I discussed about linear filtering. I discussed about how this um sorry I discussed how these images are yeah this point operation and local operation and global operation. And apart from that, yeah, apart from that, we discussed about image filtering, how you have can we leverage filters to sort of uh, achieve different tasks like sharpen the image, blurring the image, left shift and right shift. And yeah, I guess that's it for week one. There is nothing much I can discuss in this session because it's just week one, and there is not much of a content there to discuss. Half of them are just history and introductory lessons. But there is one more thing I wanted to discuss. Yeah, the convolution operation. So I'll just briefly talk about convolution operation. So the convolution operation comes from the study of signal processing, where you convolve a small signal into a large signal. Like you just take this and you just perform some operation, then you shift the signal and perform the same operation in all part of the signal. So it is not the correct way of saying this, but the idea behind that is that you convolve this small fraction throughout the all the entire data, and this thing is inside an image. And what they did is that they took an image, they decide on a filter, they put this filter here, then evaluate, then they put this filter here, evaluate, then they put this filter here. So in this way, they covered the entire image. So they like, you take a filter, you multiply it with element wise, you take the summation of it, and you will find the value for your pixel in the transformed image. So two things come into mind. One is stride, and one is, so three things. One is stride, one is padding, and another is two things, stride and padding. So I'll just discuss that briefly. What do you mean by stride and what is padding? So let's say I have an image like this. It's a, it's just a 1, 2, 3, 4, 5, 6. This direction also. Bear with me, I'll just draw some nice lines now. Yeah. Just randomly put some values. 4, 0, 9, 1, 1, 1, 1, 0, 2, 3, 7, 9, 0, 0, 1, 5, 6. Let's say my filter is 2 cross 2. 0, 0, 0, minus 1 or 1. If I put my filter here, in this first cell, I'll get the value as 4. So in the new image, my first value will be 4. And then I will shift it, and then I take this 4 values, and the value will again be 4 because it's all 0. I'm just taking the rightmost corner. If you take this, the value will be 1. So what you see that, and if you go down, the value will be 3 here. If you see this, we're sort of involving one pixel in one iteration. But if we want to do more, if we want to involve all these pixels more than once, we can take the first as it is. For the second, we sort of take from the second value itself without taking from the this value. We'll take this value so that this 4 and 3 will again be engaged in this calculation, and this value will change from 4 to 7. This is called a stride of 1. So this is called, when I am shifting the convolution, I am sort of taking one step from the previous starting point. This is called stride of 1. And also, if I go down just like that without skipping this second row, this value will be 3. It will be intact, but it will also be a stride of 1. This is the definition of stride. So how many rows how many, like entity you skip before putting your calculation? It can be 1, 2, 3, and depending upon the your requirement, you can do. So basically, but generally it is always 1. Okay. Then the stride is done. Then we will discuss about something called padding. So uh, you're done with stride, you can see that, so this 3 now will be involved in this block, in this block, in this block, and in this block. So a pixel like 3 which is sitting in between the image, it get to be a part of computation for all the neighboring pixels. But if you see pixels here, 147, 491, they are only part of 1 or 2 computation. To make it up to them, to involve them more, what we generally do, we add padding on top of it on the foreside with 0, so that this convolution operation can start from now this point. And second will be this point, and third will be this point, and fourth will be this point. Now, if you see, this 1 and 4 are also involved in 4 different computations. And since adding a white patch around the image, a very tiny, very small white patch does not affect the image property or image definition. It's okay to add white patch around the image. It will just enhance the it will just enhance the like involvement of any pixel in the final round. So so uh, so you can say that stride and padding are two different things, which as is enhancing this convolution operation that we have in hand. And it is sort of yeah, stride and padding is like sort of kind of this thing. And there is also a nice formula to calculate, like if you take a filter of, so if the initial image size is m cross n, and your filter size is say n cross n, and your stride is 1, the stride is s, and padding is p, what will be the resultant image size? That is k cross l. What will be that? So there is a nice formula to that. And if you could, so I will discuss this formula later when we're studying CNNs and convolutions. But so if you could just like if you could just assume it, you can easily you can easily make it like sort of, you can easily guess that it will be uh, I guess it will be 2 I forgot actually. It's actually uh, m minus uh, okay. I cannot recall it now, exactly recall it now, but we can discuss about this in the subsequent lectures when we're studying about CNNs and all. So this is the story so far. Like you get like you have images, you know how to represent them in the grayscale. You have this 100 dimension, 1000 plus odd dimensional in grayscale image. You have this pixels which varies from 0 to 255, and in the color images you have pixels from varies from 0 to 255, but in three color ranges, red, green, and blue. And then we learn about like how you can represent an image using image density as well. And also we learned about how do we transform an image that is given in three different ways. One is point operation by doing local operation, and then the third one is doing global operations, and uh, local operations, global operations. And uh, we also saw like point operation, an example of reversing the contrast, and the local operation, an example is moving average smoothing, and the global operation, and an example is Fourier transform. And then we discussed about image histograms. So how an image can be represented as a histogram of intensity, which varies from 0 to 55, and how you can normalize it to get percentage of pixel that is lies in a intensity. And after image histograms, we discussed about how cumulative frequency of an image density can be computed using cumulative frequency graph, and where each point will represent that what is the number of percentage of pixel that is that has at most k intensity of value k, that is it has intensity of value of k or less than that. Then we sort of talked about contrast transition, where we sort of lower the contrast of the pixels, which has lower contrast, lower intensity, and increase the contrast of the pixel, which has higher intensity, to make the image beautiful. And one popular way of doing this right is called histogram equalization, where we try to uniformly distribute the histogram that we have and make the cumulative frequency graph line uh, a straight line passing through the origin. So this is the way of enhancing an image. And then we learned about convolution, and also we learned about various filters in this slides, where I sort of demonstrated some images of histogram equalization, and also some images on filters showing filters. I mean that you use in common while for transforming an image to while convolving on an image using filters and kernels. Then we also learned about this difference between this kernels, difference between this um, separable and inseparable kernels, and yeah. So with that, I guess we have covered everything that is covered in week one. But if you have any doubt, feel free to ask me right now. I guess we have 10 more minutes left. We'll close it soon today because it's just a fast lesson and there is nothing much left like to discuss. So we'll close in 10 minutes, like 15 minutes are left. But if you have any doubt in the week number one sessions or in this discussion, feel free to type in the chat or unmute yourself and ask me. Thank you.
Hi, Subrat. Hello.
Hello. Hi.
Subrat, I am audible?
Yes.
Yeah. Can you properly define this term convolution? What is the meaning of this exactly?
Okay. So one second. So yeah, so convolution means like you take the image and you sort of find a filter and you sort of try to impose this filter throughout the image. But you cannot like sort of take a bigger filter and apply it on the image. So what you are doing instead is that you're taking this filter, you're applying on the image, and you're sort of uh, traveling, sort of dragging this filter through the image to get the effect of this filter on the image in all parts of the image. So that is
Yeah.
called convolution. Like
No,
I cannot.
Subrat, can you is there any mathematical definition to this? I mean, what you describe is the process, right? So what you
Yeah.
exactly do during the convolution operations. But my point is, do we have any mathematical definition to define what is convolution?
So actually, the convolution operator is so it's like a addition operator. The convolution operator is this. So convolution operator takes so
I think
it is
there's something called signal transformations. You were talking about something, I couldn't get it. I'm sorry, I lately joined to the sessions. You are talking to some signals or something magnified, something you are talking about
so
regarding
this is
that
actually
convolution.
so the convolution term came from the signal processing domain, but I am not from a signal processing background, so I couldn't I wouldn't be the best person to advise you on that. But I can say that they took this concept from a signal processing and they applied it to the image. I think that might be the one reason why it is very ill posed in image domain. But I will make sure to find that the exact mathematical definition of convolution in the images and make sure to deliver to you in the next session that we have in the next week.
Yeah, if you
So
can put it in the discussion forum, I'll be getting it right. I need that exact definition, mathematical, right?
okay, sure, sure. So this is the operator actually. The one I am saying is the operator where we take the filter and we just apply the operator on top of it. There is a integration based formula for that. So I'll make sure to find that and put it in the discussion session as soon as possible. People don't really discuss into this much, so I got lost. I got lost of the track. Yeah.
Okay, no issue, no issue. Thank you.
Thank you.
Hi, Subrat. I wanted to ask something. Hello, am I audible?
Yes, hello.
Yeah, yeah. I wanted to know whether this the nodes that you showed, is it available to us? Can you
Yes, so
share it?
yeah, I'll be sharing this note and I'll be sharing the PowerPoint presentation as well. So that links will be provided to you by the. So there is this. We got a Excel sheet to fill out our links to the video that we are that the session that we took now, and the
Huh.
notes that we did, or like the PPT that we showed during the session. So all these things will be shared by the NPTEL coordinator that who is
Oh,
assigned for this course.
okay, okay. We will be getting it anyway, right?
Yes, yes, yes. It will be there
Okay,
in the
thank you.
discussion session.
Yeah, sure. Thank you. Thanks for the session. It was really informative.
Thank you. Since we are asked there to record 2 hours of session, so I'll just wait for 10 more minutes for like if to stop the recording. So if but in between, if you have any questions or doubt, you can ask or you can leave the session if you want. Um, noises. 10 more minutes left to
Hello, sir.
complete this session. Thank you.
Hello. Hello.
Hello, hello, hi.
Hi,
Yeah.
sir. Can you hear me, sir?
Yes, yes, yes.
Sir, how to select the filter, sir? It may be from the
Okay.
default filter, or we can add some own value for the filter.
I see. So before this deep learning era started, people used to like create their own filters. So what they do is that they sort of like calculate and come up with a filter for extracting the edges from a image. So when they try to study an image, when they try to like sort of getting inference from an image, so what they did is that they sort of tried uh, creating filters which can extract the edges, which can extract the vertical, horizontal, which can blur the image, so that they can they can do some operation on top of it and do some image processing on top of it. But as the time progresses, so what people have realized that instead of creating these filters automatically, sorry, instead of creating these filters manually, what if they can ask a neural network to learn this filter? So, 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 so they have some underlying task that they want to achieve. They have some task they want to achieve. Let's say for classification, for classifying this set of images into cat and dogs. So what are the filters that is necessary so that it will extract the essential features? So earlier they used to extract these features by handcrafting these filters, but after the deep learning era, what they have done is that they have they have asked the algorithm that okay, this is the task in hand. Like you have to classify cats and dogs. What is the necessary features, filters that can be applied to the image such that it will give us very informative features in the as an intermediate step. You please decide. So they just asked the algorithm to design the filters. So in this way, the filters are sort of learned in terms of algorithm by for for the particular task. So earlier, yes, there used to be filters, but nowadays there is nothing that is something called filters. People are sitting and designing. What they are doing is that they are just asking a learning algorithm to sort of find them a filter for this task. So it's kind of getting generated now implicitly without any human intervention or without any human expertise in that area. Yeah. Is that answer your question? Does that answer your question? I hope so.
Yes, sir. Yes, sir. Thank you. Thank you, sir.
Thank you.